into a little, I want to say it was a 1x1 box.
Yeah, I would
in
agree.
the bottom right corner, right next to your parent's signature. And I'm like, my mom taught me how to forge her signature because she was tired of looking at this.
Oh my word.
So.
Yeah, so anyway, you guys are mostly going to miss that poor Malia. And so anyway, but yes, this is part of how we adapt. When things aren't working well, we find out, we fix it. So next year, everybody's going to have to learn how to be organized. And then you'll get a certificate that if you don't lose the certificate, no, I'm just kidding. I know beyond your diploma, I believe on your transcript or your diploma, it'll mark that you got that.
They know how to check their email.
Well, no, it's like going to be, I think it's like a certification in time and resource management or something like that.
What kind of bullshit kind of thing is that?
Because you'll be better off than the people who don't have it. Alright? Alright, I want to talk. I want to chit-chat. This PowerPoint, by the way, will be available to you, actually is available to you on It's Learning, because I know sometimes that's useful to people. And we've been learning about statistics and ways of making descriptions of things using statistics and how likely things were. Last time we were doing that normal distribution stuff where we could actually figure out the probabilities of like certain measurements and so on. And I want to talk about an application of that. We're on to, but I think we are. And in the beginning of section 9.4, the author proposes a problem. He says, suppose we're watching this traffic go by, we got a radar detector, radar gun kind of thing. And we are saying, I wonder how many cars are speeding. Now the truth of the matter is that would be a really difficult thing to do, to measure. Because those things are manual. I don't know what you know about radar guns, but they don't like sort of scan across all the traffic and figure out how everybody is doing. It's actually done manually. They literally have to sight it in on each car as they go by. So it would be quite a challenge to do this as a couple hundred cars go blowing past, right? That would not be really something that could be done. It's really good, actually getting a count of, oh, I see 712 of these cars were speeding, would be really hard. And honestly, that's not exactly the information that we want anyway. Probably closer to what we want is what fraction of these cars are speeding. Now, okay, I can imagine that we could do that. In fact, I would imagine that that's been done. Okay? Often it's the case, for example, that on overpasses, there is a radar gun that is just shining down, and just for monitoring of traffic, they're counting and seeing how many cars are moving how fast. This is part of like how the city knows when there's traffic jams and stuff like that, okay? Long before anyone has called and said there's been an accident, they already know traffic is not moving on the freeway, okay? Because the machine already has detected nobody's moving, that kind of thing, okay? So they probably already have some idea of what fraction of the cars are moving at certain speeds and so on. And in the problem they propose, suppose we already know that 40% of the cars are speeding. Okay, just from some routine monitoring or something like that. So that part of the answer we already have. But that's not exactly what we would be wanting. Let's say you are now the police officer, you're up here on the overpass, you've got your radar gun, and you're shining down. What you're wondering is stuff faster than usual today? Is it unusually weird how fast the traffic is moving? And what you did is you took your radar gun, sitting down. Never be afraid of the cop who's up on the overpass, by the way. How the hell is he going to get you? Right? My wife hits the brakes every time there's a cop on the overpass. You know what I'm saying? Like somehow or what? He's going to rappel down like a Navy SEAL coming down to get you at you zip by at 70 miles an hour. There's no way he's not going to get you up from up there. He might measure you. You're going to the logbook, but what's he going to do? All right? So you're up on the overpass, and you have measured 100 cars as they went by, and you found that 50 of them were speeding. Is traffic faster than usual today? That is a piece of information cops need. Okay? Now, I think we can agree that if normally we know that 40% of cars are speeding, we would have expected 40 of the cars to be speeding, right? There's actually a way, using the binomial theorem, we could have actually proven that to ourselves, but I think just common sense tells us that, right? If 40% of the cars are speeding, out of 100 cars, we would have expected to get 40 cars, right? Aren't you grateful, Malia, you didn't have to actually prove that? All right, great. All right, and you would agree that it is just by chance how many you get in a given day, right? I mean, if he measured the next 100 cars going by, he'd get a different number than 50, right? It's just chance. Just like the other day when you were rolling dice. When you were rolling dice, sometimes you got bigger numbers and sometimes you got smaller. It wasn't like some other dice were loaded or something, or I was cheating, right? You just sometimes get more and sometimes you get less. It's just chance. So the question is this unusual? Would this happen very much? If he measures 100 cars and 50 of them are speeding, is that all that rare? Or does that mean, because if it's rare, it means that apparently traffic is faster than usual. So here we're saying, I measured 50 cars out of 100 that were speeding. Is that really all that unusual? And this sounds like a binomial theorem problem. I mean, effectively, we have a success and failure. We'll say success is they are speeding. The alternative is they're not speeding. 40% of the time will be successful, they're speeding. Okay. Well, you might remember that the binomial theorem is about finding the probability that your value x, how many successes you had, was equal to, in this case, 50. And it's this formula. This is kind of an old friend now. We've done that formula from everything from rolling dice to raffle tickets to dartboards. I don't even remember what all we've done with it. And in this case, then we'd be plugging in that n, the number of trials, was 100. 100 times we aimed the radar gun at a car, and we want to have 50 successes. Combinations of 100 things taken 50 at a time, times p, the probability that any given event will be a success. That's 0.4, because there's a 0.4 chance that we will be speeding, raised to the x power, which in this case is 50. And I have a misprint on the slide here. I have 1 minus 0.5, but it's 1 minus 0.4. Okay, because that's, remember, 1 minus p right here to the 50th power. Lisa, how do you feel about that equation?
Good.
You feel good about
I
it?
think the only kind of confusing part is the 100 comma 50.
100 comma 50. How do we do 100 comma 50? It's going to be 100 factorial over 50 factorial times 100 minus 50 factorial. Holy crap. I mean, we like those equations because they cancel all over the place. Except, remember how that pattern works? You do 100 times 99 times 98 times 97 until you get all the way to 50 times 51 times 50 factorial. And that'll cancel with the 50 factorial in the bottom. But notice what you still got in the numerator. 100 times 99 times 98 times 97 all the way to 51. Holy crap, this number's going to be huge. And not much fun to compute. And I don't really love doing things to the 50th power either, but then again, that's just going to be a calculator thing. But here's the deal. This is a mess. But you know, I mean, it actually could be done fairly easily. Well, not so much easily, you have to know how to do it. But on a spreadsheet, you could do this. Because, remember, on a spreadsheet, we've got that equals combin function that equals combin 100 comma 50, and it'll give it to you. By the way, it's times 10 to the 29th power. It's a rather large number. But that's okay, because you know what? 0.4 to the 50th power is a really little number. And this works out to 0.6 to the 50th power is a really little number. So it's going to be fine. In fact, if you do the math, you get a whopping 0.01, roughly 1%. You have a roughly 1% chance that you're going to get 50 cars. MJ.
Yes.
How did you feel about that number? We're sitting up there, bing, bing. We're the cop. We're the man. We're the fuzz. We're the pig. We're up there on the I should not have said that on YouTube video. And we've got the radar gun and we're shining it down there. There's a Muppet sketch where they say that. I'm the cop. I'm the man. I'm the fuzz. I'm the P-I-G. Anyway. And he is shining the radar gun out there and he got 50. Would you guess that it'd be as small as 1%?
Probably not.
Seems kind of tiny. Anybody got to guess why this number's so tiny? We did something kind of weird here that wasn't quite what we meant. I'm going to tell you what's wrong here. We didn't make the question right. That is the right answer. That is the probability that we're going to get 50 cars. But Andrew, what do you think?
Because it's specifically 50 cars?
Yeah, what about 51? What about 52? What about 53? All that should count as 2, right? When I said I got 50 cars, what I really meant was 50 or more. Right? What are the odds I get 50 cars? What I really mean is, how weird is it? I mean, it just, this is only the probability of getting 50. It's not really what I mean at all. What I really mean is, I measured 50 cars out of 100 to be speeding. What's the probability that I would get 50 or more cars that are speeding? Andrew had it exactly right. Because, I mean, the odds of getting exactly 50 aren't that great. Same with when you roll the dice. Remember, you could get a number up to 60 by rolling those 10 dice. And, oh my gosh, I got a 45. Is that an exotic number? Well, any number. 40, the expected value, remember, the mode. The most common one was 34. Do you remember that? And even 34 wasn't that much. It was like 1% of the time, right? What you really mean is that or more. All right, so we can do this. Now, once again, this is a binomial problem. Oh, we did this. You did this on one of the problems on the test. Where you had something like, I don't even remember. Something was going to happen 10 times. And you were going to pick I don't think it was ties. Let's say it's ties, though. You got ties in the drawer. You got, there's blue ties, and there's a blue tie and a red tie in the drawer. You're just going to reach in the dark and grab a tie. Okay? You're either going to get the red tie or the blue tie. What are the odds you'll get the blue tie 8 or more times? Well, what that means is, what's the probability you'll get the tie 8 times? What are the probability you get the blue tie 9 times? Or what is the probability you'll get the tie 10 times, right? You actually did the math 3 times on there. You did the probability that x is equals 8, the probability that x equals 9, and the probability that x equals 10. Well, it sounds like we can do that here. It sounds like what we ought to be doing is, if we previously had computed the probability that the number of cars was equal to 50 and we did all this, what we're going to really need is the probability that the number of cars is 50, plus the probability the number of cars is 51, plus the probability the number of cars equals 52. Holy crap! All the way up to 100. I didn't love this problem when it was 1 time. Now I got 50 times of it. I am not loving that. If you did this using paper, and you sat there and had to compute those combinations, remember how much we didn't love it? When we had to do 100 times 99 times 98 times 97 times all the way down to 8 times 51? Now you can do that for that, and then to 52, and then to 53, and then, oh crap, nobody's going to want to do this. But of course, once again, in reality, with a spreadsheet, this is doable. We're going to use that equals combin function, and a bunch of lines on a spreadsheet. And I'll show you that in just a second. But actually, as you'll see when we do it in the sheet in just a little bit, the answer works out to 0.271. About 3%. MJ, how do you feel about that number?
That's a lot better.
It's certainly bigger. And when there were 40%, when 40% of the cars are speeding, 50 or more getting caught, maybe 3% is not a bad idea. You would kind of expect it to be more like in the 40s. In the 30s or the 40s, right? More than 50, maybe this is... I'm not hating this answer. I like the fact that it went up when I included 51 and 52 and 53. And you know what? That included when 80 cars were getting caught. How often do you think we caught 80 cars speeding if 40% of the cars are speeding? That would almost never happen, right? I mean, even though we're adding it in, that's probably getting pretty damn close to 0% probability, right? What are the odds that 100 of the cars were speeding that we measured? That's going to be so damn close to 0, it's hardly worth adding it in, right? But let me just show you the spreadsheet real quick. Here's literally a screenshot of how I did it. I made my table here, where x was equal to 50, x was equal to 51, x was equal to 52. For each of them, I computed C, the combinations. That's because it's literally just a screenshot of the PowerPoint, the Excel spreadsheet. I can't like put my mouse over here and show you the function, but it's equals combin 100 comma x. All right. That middle term was just 0.4 raised to the x power. Notice how tiny it is, holy crap. And that last term was 0.6 raised to the 100 minus x power. All right. Then my actual probability then is just this times this times this, and here it is. So this is the probability that x is equal to 50. This is the probability x equals 51. This is the probability x equals 52, and I did it all the way down here someplace where it's equal to 100. Added all those probabilities up, and I got the sum right there. It took me a few minutes, but it wasn't the end of the world. But it was a lot of work. And it took a fair amount of knowledge of how to do the combin function and how to get the cell references right and so on. I made a few mistakes along the way as I was doing it. And once I actually had it, I said, you know what, I've done all this work. I now have, for each value of x, I have the probability of that x. Maybe I should just use this information to make a graph. Maybe I should make a graph that shows for each value of x, what is the probability I get that value? So what is the probability I got 40 cars? What is the probability I got 41 cars? What is the probability I got 42? All the way out to 100 cars. And in fact, it's not that big of a deal. I can make that graph and it's right there. Oh, wait a minute. First off, some of the things make a lot of sense about this graph. For example, notice the mode. The mode being the observation we're expecting to see the most times. The one with the highest probability. Remember on this graph, this is the number of cars that we observed out of 100 to be speeding. And this is the probability we'll observe that number of cars. And unsurprisingly, the most likely number is 40. If 40% of the cars are speeding, the most likely number is 40. But you'll see actually it's not that high, right? Even that's only like 7 or 8%. Unsurprisingly, it's very rare that we're going to have small numbers of cars that we catch. If 40% of the cars are out there speeding and I'm out there on that beam and I get 20, that's weird. Or I get 25. Look at this. It's the odds that I would just happen to only get 25 cars is not very good. Traffic is slow today. Not very many cars. I can catch very many people speeding. Unsurprisingly, it's very rare to get like 50 or more cars speeding. If 40% of the cars are speeding, it seems weird if I get 52. Sounds weird. I think more than 40% of the cars are speeding if I got 52. Right? Because it's so unlikely I would have gotten 52. Huh. In fact, when I was asking the question that was up there at the top of the slide, I measured 50 cars speeding. What are the chances I would get 50 or more speeding cars? What I really meant was I'm adding up these bars. Probability of 50 cars, probability of 51 cars, plus probability of 52 cars, plus the probability of 53, all the way out to out here by 100, although the bar gets pretty darn little by the time we get out here. Ha! Okay. Okay, I can see graphically, see how the graph helped us understand what I was doing? But here's the deal. I mean, that was just what I said here. So what I was saying originally was I literally added up this probability, plus this probability, plus this probability, plus this probability, and it was a huge amount of work. It was way too much work to do on paper. It was way too much work to be doing tip-tap on your calculator. It was really a spreadsheet kind of problem. But here's the deal. Oh, I set this joke up for the last like 30 slides. That shape should ring a bell. Poor Lisa, she doesn't grow. Right? Doesn't that look like the bell curve? It sure does. In fact, French mathematician Pierre-Simon Laplace, who died in 1827, was the one who proved the binomial curve and the normal curve are kind of the same thing. Lots of things in math are named after Laplace. But you don't usually get to that until like calculus classes. But Laplace was the guy who came up with central limit theorem? No, what is that called? I think it's central limit theorem. Read over here and tell me, is it down here maybe? Central limit theorem is the one that shows that this is true. It's actually even more general than that. But the central limit theorem is how you show that this is true. That the binomial theorem is just sort of a way of saying the normal curve. Which kind of makes sense. I mean, in the end, wasn't the normal curve, like when we were talking about test scores are distributed as a normal curve, or whatever, wasn't that really just a way of like measuring how many people got to a certain level? I mean, if you set the level at, on the ACT, a 27 is a pass and below a 27 is a fail or whatever. I mean, we would call it pass and fail, but like as in you were successfully got to 27 or you didn't successfully get to 27. Isn't it really kind of just a binomial thing? It's not really all that surprising that those things work out as being distributed normally. So it seems like all that stuff we did for today using the normal theorem, the normal distribution should work. For example, let me just take that same, this is literally the same curve here. All I did is I went into Excel, there's a place where you can set it where the curves, the bars don't have any space between them. So I just set it that way, okay? So they look more like the bell curve that way. And the bell curve, you can picture it coming through here like this, right? It doesn't quite look like this. The bell curve is smooth. It is not step, 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 step like this. On the other hand, if I had taken more cars, more than 100, so we weren't just talking like out of 40 here, but this was getting bigger and bigger, these little steps would be getting narrower and narrower and narrower. And in fact, as the population n got bigger and bigger and bigger, each of these little steps would be getting narrower and narrower, and they'd be approximating a smooth curve. Thank you, Simon Laplace. Simon Pierre. Is that his name? Simon Pierre?
Simon Pierre.
Yeah. Now.
Or Pierre Simon.
Pierre Simon, okay. Pierre Simon. Alright. I mean, this looks like a normal curve. It seems like the tricks we learned last time about working with normal curves should at least not be terrible guesses. Let's look. So for example, if I could come up with like a z-score, like you did for today's assignment, this case being the z-score associated with 50, where 50, we mean 50 cars out of 100 were speeding. If we could come up with the z-score for that, and we will in just a little bit, then what we would say is, look, that little table in the back of the book on page 813 would give us the problem. Remember, that's what the caption of that table is. The area to the left of that value of z. So if we could come up with a z-score here, it would tell us this area, the red area on the graph, the probability of getting 50 or less, and then we can just take 1 minus that, the complement of that, that would be the blue area. The area to the right of z, which would be the probability of having 50 or more. So if we could just come up with some kind of z that would be a measure of the weirdness of 50 compared to an average of 40, those curves on the back, those numbers on page A13 and A14 will give us everything we need. It won't be right. Students hate it when answers aren't right, but it'll be a damn good approximation. Let's do that. In section 9.4, they actually give you the formulas for computing z. Well, z is no different than it always has been. Z is just the observation we're talking about, in this case 50, minus the mean divided by the standard deviation. Well, that we don't know yet. Well, the mean, the book gives us, is just n, the number of observations we have, times the probability of success. Well, if n is 100, we measured 100 cars, and each one of them successfully could be speeding is 0.4. 100 times 0.4 is 40. So the mean is 40. The book in section 9.4 also gives you how to compute the standard deviation of a binomial like this. And its standard deviation is this weird formula, square root of np times 1 minus p. But you can plug in the value of n, 100 cars, and p, 0.4. There's a 0.4 chance that they are successful, in the sense that they are successfully speeding. And you get that the standard deviation is 4.90. So, we have that sigma, the standard deviation, we have that mu, the mean, and from that we should be able to compute a z-score for 50. That is this line right here. What is this place right here on the bell curve? And it is x, which is 50, the number we're working with, minus the mean divided by standard deviation, and you get that z is equal to 2.04. First off, let's use a little number sense. Does that number make sense? That would mean that we're a little more than 2 standard deviations from the mean. Well, if our mean is 40 and a standard deviation is right around 5, we're right around 2 standard deviations from the mean. That makes sense. All right, we've got a good answer here. All right. So we can go to the back of the book on page A14, I believe. And we can look up 2.0 in the rows and go over to 4 in the column, so that we got 2.04. And you find out that the area to the left of the curve, the red area on the graph, is 0.9793. 98% roughly of the graph is over here. The area to the left of the graph is that giant chunk. Which means that the blue chunk, which is what we want, that all those areas over there, comes to 0.0207. The blue area on the graph, that's what we needed to know. So this idea of using the normal approximation told us that the probability of getting 50 or more cars to be the ones that are the ones we need, that are faster than that are speeding. Sorry, I was being very articulate. I was thinking about the next slide already. Using this normal approximation, which wasn't that hard, compared to all the math of making this damn graph, where I did the combinations and I had to figure out the probability of this, and the probability of this, the probability of this, the probability of this, which was a ton of work. This normal thing was easy. All I did was compute the mean and the standard deviation, which were those 2 really easy little formulas. From that I got z, and then I looked up in the back of the book how to get from z to get this probability right here. And here's the deal. I got 0.02, about a 2% chance that we would have a number greater than 50. And remembering, this is the old slide I just brought back here, in the old binomial theorem we got 0.027. Okay, we're not like spectacularly close here. Like, the percent error is actually not tiny. But actually, this is not so far off, right? Our answer using the binomial theorem came up to this. Our answer using the normal approximation came to this. They're not so far off. Here's the ugly truth your book neglects. There are ways to make this better. And a stats major would have a whole chapter, if not a whole unit of the course about this, about ways to have adjusted the normal approximation to get these closer and closer. The book isn't going that direction with it, thank God. We got lives to live. Go and be a stats major if you want to know how to do all that stuff. This can get you much closer answers than what we just got. Okay? But it takes more techniques about how to make these bars narrower and stuff like that. So if you think of this as that close of an answer, I agree. But it's a pretty good approximation. If you didn't know, Andrew, what to even guess as to what the answer would be. When we started this lecture and we said, I should have asked, what do you want to estimate the answer is going to be? If 40% of the cars are speeding, what is the probability of getting 50 or more? The fact that we got two slightly different answers, one is basically 2% and one is basically 2.7%, those are pretty damn close, right? Because somebody would have said 25%, and somebody would have said very, very tiny numbers, right? They're in the ballpark. Your book is happy that these answers are in the ballpark. There are techniques to get even better answers, but we're not going to do them. Hey, while we're at it, remember that we had earlier, this is again just a slide from earlier in the text, either earlier in the lecture. What about that possibility we had where we talked about exactly 50? Remember how we accidentally stumbled upon that first part of the problem where we did, what is the probability of getting exactly 50? And later we decided that wasn't even what we wanted. Well, we could have done this using the binomial theorem too. So the normal approximation too. And I'll show you that in just a second. But let me help you understand. So there's two different kinds of problems we can be using this normal approximation to solve. One is when we have some threshold and we mean I want bigger than that. Or I want smaller than that. Or whatever. Okay? Then this is for the kind of, that's what we've been doing now. That's what we had been doing. Right? We wanted 50 or more cars to be speeding. Now we mean an exact number. The technique I'm going to show you now is when we mean, what is the probability the number is exactly 50? And you'll see in the homework set there's some of each kind of problem. Okay, so if you've got, what is the probability that we get exactly 50? Well, once again, this is going to come to us from our idea of saying a graph of these probabilities is going to look like the normal curve. So like, for example, if I was looking at this graph that showed the probability of getting 40, the probability of getting 51, 42, 43, all the way up here, what I mean is, what is this little chunk right here? This little piece right here is the area I mean. What is the probability of getting that one? Notice he's not real big. He's so little, we should zoom in on him. My 8-year-old was watching me make this PowerPoint and he's like, you put too much crap on a slide. And I said, I do put a lot of crap on a slide. And don't take a time out for using the word crap. So we're just looking at this little piece here. I want to know what's the probability I land on this. You know, what is the probability? I don't mean 47, I don't mean 48, I don't mean 49, I don't mean 51, I don't mean 52, I mean this one. And what I want to show you here, if you look at the x-axis here, 50 is sort of like picture it as sort of like the middle of this bar, and 49 is over here, the middle of this bar, and 51 is the middle of this bar right here. Well, if you thought about it that way, what I mean is this little chunk right here that I have bounded by these x-axis. And my son said after he gets that time out, you put more crap on those slides? And I said, you ain't seen nothing yet. And you put these lines here. Can you see how this line would sort of be like at 49.5? And this line is like at 50.5? If the middle of this bar is 50? We're talking about the chunk that, like on the graph, the x-axis, that little red bar is sort of like from 49.5 to 50.5. So if we could come up with z-scores for 49.5 and 50.5, we could play the whole normal distribution again. Alright, well it turns out, alright, we've got, I have negative here, but obviously it's not negative. For 49.5 and 50.5. Well, okay, we got these formulas up here. I left them up there as crap on my slide for a reason. Alright, we've got the formula right here for this and for that. And hold on, let me just double check that that's not. Oh man. I've got a kid home from school today. Everybody's good. Okay. So, we could actually come up with, I mean, if we know the mean is 40 and we know the standard deviation was, I think it was 4.9, we could actually compute z-scores for each of these guys. And this guy's z-score is 1.9 something, and this guy's z-score is 2.14 something. We actually have these two z-scores. In fact, let me put them onto the graph like that, just so you can see. This is this z-score, this is this z-score. We got lots of tail over this way, we got lots of puppy of the distribution this way. So the little area between those two, that little red area in between, at this point my son was, you're just doing this to be weird at this point, to put more crap on the slide. I said, no, it's education. Go sit and time out again. I said, this area that is red, a way to figure out this area that is red would be, it is the area to the left of this line, which the back of the book will give us, right? If I look up this z-score in the back of the book, it will tell me the area to the left of this line minus the area to the left of this line. Slick! All I gotta do is look up this number's to the left of, and this number's to the left of, and I'll say to the left of this line minus to the left of this line gives me the red area. And in fact, that's not that big of a deal. You can do it in the back of the book and you get 0.0107. And I will let you look those numbers up if you want. So the probability of getting 50, according to the normal approximation, is 0.0107. About a 1% chance that you'd end up with 50 cars. Now remember, earlier in the lecture we actually did all the stupid math using the, again this is a slide you've just seen before, I just made some new thing on top of it here, and you got 0.0103. That's not bad at all, right? Our original estimate was the right answer. The binomial theorem tells us it is 0.0103, and this normal approximation in this case came up with a pretty damn good answer of 0.0107. I mean, we're only off by a few hundred, is that hundreds or thousands? I'd have to think about it. We're very close. Thousands, I think.
I think it's 10,000.
Yeah, more than
10,000, yeah, we're very close. In this case, the normal approximation was super duper good. But anyway, so see how we solved a different kind of problem here? But both of them, what we really did was we took something that's distributed binomially and said, normal is going to be close. And we said this value of x, that we are, you know, like 50 cars or whatever, we can just convert that to a z-score and then just use the normal distribution, and it's going to be close-ish. It's going to be better the bigger the value of n is. For smaller values of n, there's corrections we could do, but again, thankfully the book doesn't go that direction with it. Because like I said, that could be a whole unit in like a stats class. That's a big deal. But this is pretty slick. In 35 slides, it's not obvious how much of a time saver this is. But compared to computing those spreadsheets with all those combins and stuff, and all that, this is a hugely easier way to do it. In fact, I'm not even going to make you do those. Doesn't that seem not like me? You could see the dread on Andrew's face for the last 15 minutes. I was going to be making a big Google Sheet spreadsheet assignment where he had to do all that. Trust me, I thought about it. But then I thought about Thanksgiving. And I thought about how the whole point of this is easier. So I'm not going to make you do all the spreadsheets and stuff like that. If you want to, hey, that's awesome. All right. Instead, you just have this relatively little assignment. What did you say? Sigh of relief?
Sigh of relief.
All right. So, you have this relatively little assignment here. And, yeah. I think you'll get this in pretty fast. All right. How did the assignment for today go?
I don't remember.
Good.
I didn't feel like it was all. I didn't get. Usually, I get at least somebody to send me a stressed out email about it, and so I wasn't sure. That probably meant good though. And if you have questions about it, obviously let me know. All right, I'm going to stop the recording, and what we're going to do